Hey everyone, myself Gayatri Soumya. I am a senior machine learning engineer at GoML. As part of today's GoBuild episode, we are going to discuss on building production grade RAG applications. This isn't a tutorial on what is RAG, most of you people know that. So we'll speak about the architectural decisions, the tooling trade-offs, the real implementation patterns we have used across multiple RAG application deployments, what we learned, and we'll cover everything you need to know to harden a RAG system for production. We will first start on when to use RAG, and then moving through the full ingestion and retrieval pipeline, and then also talk about deployment and evaluation. I'll call out specific decisions we have made in our production systems throughout. So let's start with the most important architectural question. When should we actually use RAG versus alternatives? RAG is the right call when your knowledge base is dynamic, like it keeps updating daily or weekly, and when your data is proprietary, that is, it was not part of the model's pre-training corpus, or when you simply cannot tolerate hallucination. RAG is also preferred when you need source traceability, such as in domains like legal, healthcare, finance, RAG applications. Now, coming to alternatives. Fine tuning is preferred when your knowledge base is stable, it doesn't change much. While long context is expensive and retrieval is unstructured, and prompt stuffing hits token limits, and it actually degrades as the document count grows. So, to conclude, RAG wins on freshness, cost, and auditability for most enterprise document QA workloads. So fine tuning is better when you need behavioral adaptation rather than knowledge injection. So here's the end-to-end pipeline at a glance. So we've got 6 stages. So the input would be raw documents, and then we have parse and extract, chunk and enrich, embed and index, retrieve and re-rank, and then generate. Each stage has its own tooling, trade-offs, and failure modes. Let's walk through each stage in detail. So parsing. So parsing is where most RAG projects underinvest, and it's often the root cause of poor retrieval quality. And I have encountered it in one of my projects. So for standard PDFs and text docs, Pioneer PDF is fast and reliable for text, image extraction, and simple table extraction. While Docling gives you structured layout-aware parsing if document structure matters. When it comes to enterprise mixed content documents, the ones with embedded tables, scanned images, charts, plots, figures, all on the same page, we used unstructured.io in most of our projects. So it locates element boundaries and classifies content type. Like it would be able to locate text content and then table and then images. It is also used to identify the layout. So the key move that we made is that instead of just taking the unstructured raw output, we passed each identified table and image element to an LLM to extract the structured content. So for tables, it means that getting proper row column semantics. While for images, it means generating a descriptive caption that became searchable text when querying. So this single change, which is LLM assisted extraction on top of unstructured IO's output, gave us a measurable improvement in retrieval precision on documents with mixed content. Then comes scanned documents. So AWS extract is the production grade choice we prefer. It handles handwriting, forms, complex layouts. While for lighter weight OCR needs, we use Tesseract, but other paid OCRs as well. So for any use case, structured content extraction matters the most. Next is chunking strategies. So chunking is one of the highest impact decisions in your RAG architecture. You get it wrong and your retrieval is fundamentally broken, and no amount of re-ranking fixes a bad chunk. There are multiple strategies starting from fixed window chunking, It is fast, simple, but is context blind, not preferred much. Then comes sliding overlap chunking. It adds token overlap between consecutive windows to preserve boundary context better than fixed window chunking. Then comes semantic or section chunking, mostly preferred. It splits at natural boundaries like headings, paragraph breaks. It gives you semantics, and we usually recommend it. But we have used hierarchical chunking in most of our projects. So, how is it implemented is that based on the pattern and layout of the document is split into document title, section, and then paragraph. So each level is a node in a tree. And then fixed chunking is applied within each paragraph node if it exceeds the chunk size. So this means your retrieval operates at the most semantically meaningful granularity available, and you can retrieve at multiple levels depending on the query complexity. Now, when it comes to special content types like tables, so for tables, each chunk must include the row header and column header context. A row without its header is semantically useless to an LLM. While for images, they're extracted separately. An LLM caption is generated. The caption is chunked with an image reference. Now this becomes first-class retrievable content for images. And for scanned documents, an OCR is applied first and then filtered by confidence threshold so that irrelevant, low confidence chunks are ignored and only meaningful content is added to our knowledge base. Coming to embedding models, selecting an embedding model is often treated as an afterthought, but it shouldn't be. There are factors to decide in selecting the embedding model. The first is vector dimensionality. Higher dimensional embeddings, capture finer semantic distinctions and improve retrieval recall. But they increase index storage and query latency and cost. For general purpose workloads, we usually prefer OpenAI's text embedding 3 large or Cohere's embed v3. The next critical decision point is the domain. Like if your domain is medical, legal, or financial, using a domain specific embedding model is the best decision. We have actually seen retrieval recall improve by 20 to 30%, switching from a general to a domain tuned model on medical document QA applications. So regarding vector databases, the primary factors of choosing VectorDB are the specific use case, data scale, and operational constraint. So Pinecone is preferable for high traffic, scalable production deployments. It auto scales, has built-in embedding inference, and gives you very low query latency. When it comes to open search, it is preferred when you need hybrid search, like combining keyword matching with vector similarity in a single query. So when our workload has both keyword sensitive and semantic query based searches, then OpenSearch KNN plugin can give that. So regarding PG vectors, when the document corpus is already in PostgreSQL, then PG vectors can be used so that no additional infrastructure needs to be set up. And MongoDB Atlas is preferred for document native semi-structured workloads. If the chunks are already in JSON and the application already uses MongoDB, the operational simplicity wins. Now coming to top K tuning. So you can start with a lower value such as k is equal to 5. And for complex multi-hop question, it can be increased to 10, 15. So for precise factual lookup, it should be reduced to a lower value like 3. So higher K means more candidates for the re-ranker, but it also means more latency cost in the generation step. So it needs to be tuned empirically on the evaluation set. So now comes re-ranking and LLM configuration. Talking about re-ranking, it is an upgrade you can make after basic RAG is working. It's not a mandatory step. But with vector similarity, it retrieves relevant documents. But re-ranking is where precision gets covered. Cross-encoder re-ranking is a traditional re-ranking method, and LLM-based re-ranking gives you the highest accuracy of any method and also the highest cost. And we use this selectively for complex queries where we have already detected low confidence in the retrieval step. Then comes system prompt configuration, which is the most critical step in the RAG pipeline. So we use a set of uh, pattern and steps uh, for RAG in production. So first is the explicit role and task objective definition. Next comes step-by-step instructions for the task and enforcing addition of citation and reference in the responses. Third one is providing few short examples for the output format, and then chain of thought instruction for complex reasoning, and lastly a self-validation step. So this instructs the model to verify its answer against the context before outputting. Now, these set of steps actually prevents instruction drift in long prompts. Without this structure, the model tends to ignore the detailed instructions by the time it reaches the retrieved context. Then about context length. So context length size has to be decided based on the latency requirements of the use case and the application. Don't overfetch context just because you can. Regarding model choice, we prefer Claude Sonnet for complex reasoning and instruction following, while Mistral for high volume, cost sensitive pipelines where throughput matters more than the edge case reasoning quality. So, coming to advanced rack topics, the first is guardrails. So, guardrails is not optional for enterprise deployments, it's a mandatory step. It has to be deployed for both input and output validation. There are available guardrails, but even proprietary guardrails can also be used. It should be used to block PII leakage, toxic content, and prompt injection before they reach your LLM. Next comes session memory, that is for the model to be able to remember the chat history and then respond to new user queries. There are different strategies to preserve the session memory. First, the sliding window. It preserves last end turns in conversation. The simple and works for most use cases. Summarization, it compresses older turns using another LLM call, but it trades latency for content density. Coming to storage of charts, the DynamoDB is a preferred choice as it is a key value based storage and usually usually a good choice for chart history storage. Coming to multi-tenancy RAG systems, so this is where the users can query from the documents, only from the documents they have access to. And this can be implemented at the metadata filter level. So every chunk has some metadata associated with it, like tenant ID. So every query filters by the tenant ID at the vector search layer itself. And then the relevant chunks are retrieved from the permitted documents. So this metadata filtering should not be applied after retrieving chunks, but before retrieving the chunks. So it is always wise to add permission checks before retrieval. Next, coming to multi-language documents. So it is preferred to use language specific or multilingual embedding models to embed chunks of different languages. So the languages are redirected at ingestion time and then stored as metadata, and optionally language aware re-ranking methods are preferred. Coming to hallucination control. So there are 3 levels that can be implemented. First is grounding prompt, like explicitly instruct the model to answer only from the provided context and to say I don't know when the context is insufficient. Next would be to tune top K and re-ranking thresholds to avoid low confidence chunks entering the context. And lastly, to enforce citations. It requires the model to reference source document in its answers. Next, coming to evaluation. So evaluation is a prominent step or component of any application. So evaluation is usually done with Raga's framework. The 4 metrics that we track are faithfulness, answer relevancy, context precision, and context recall. So these metrics are implemented and automated as a regression test in the CI pipeline. So any change in any component, it like chunking strategy, embedding model, or prompt that degrades any of these metrics are blocked at deployment. So regarding deployment and monitoring, we containerize all pipeline components with Docker. So embedding inference runs on EC2 along with ECS and or EKS for scaling. The query path is a fast API service which runs behind API gateway with rate limiting and auth at the gateway layer. While for bursty or cost sensitive workloads, AWS Lambda is preferred for retrieval and generation steps. When it comes to monitoring, Raga's metrics are run on a representative eval set as a scheduled job. So we track latency at every stage. The token counts per request and retrieval scores for top K chunks are all logged. All right. So let me leave you with the 5 things that separate production RAG from prototype RAG. The first one is parser. Parser choice is not a commodity decision. Using appropriate parser plus LLM assisted extraction on mixed content documents is a meaningful lift over just naive text parsing. The second one is structure aware chunking at ingestion directly improves retrieval precision at query time. Third one is use the smallest model that meets your recall requirements. Switch to domain specific embedding models for specialized corpora. Fourth is re-ranking. Re-ranking is your precision multiplier. It's not a mandatory step. It's an upgrade after basic RAG is working. Finally, instrument everything from day one. RAG's metrics, token accounting, and retrieval score logging, these are not optional. They are your feedback loop for every tuning decision you'll make. And that brings us to the end of our deep dive into RAG implementation. We covered a lot of ground today. The key takeaway I want you to leave with is that RAG is not one thing, it's a pipeline. It's not just a vector search. A great LLM won't save you if your retrieval is poor, and great retrieval won't matter if your chunks are broken or your embeddings don't fit your domain. So as you take these concepts back to your own implementations, I would encourage you to do these 3 things. Evaluate early, evaluate often, and log everything. Every query in production is a signal. Use it. Hope you enjoy the video and thanks for watching. Bye-bye.